So, we welcome you to this new video session which is concerning light. This is a continuation of what we have presented in the previous session on nature of light. In the previous session we discussed about the nature of light and how people thought about nature of light over a period of several centuries, and at the end of that session we realized that light behaves as a wave. Now, in this session we will be discussing about what kind of a wave is a light wave. So, you know that way back in the 17th century, Sir Isaac Newton came up with this idea that light is actually composed of particles. He called these particles corpuscles. So, this is also known as the corpuscular theory of light. Many of his contemporaries, particularly Thomas Young and Christian Huygens, showed that light could also be thought of as waves, and they tried to account for some of the observed phenomena involving light by assuming that light behaves as a wave. But Newton was also successful in accounting for some of the properties of light, some of the phenomena concerning light, by assuming that light was composed of particles. And somewhere around the end of the 19th century, Augustin Fresnel, we will be talking more about Augustin Fresnel a little later in this particular session. Augustin Fresnel, towards the end of the 19th century, firmly established that light is a wave. So, he proposed a wave theory of light, and which was accepted by the scientific community because it was very strongly built on some theoretical foundations and also supported very well by certain experiments. So much so that after Fresnel's work, Newton's idea of corpuscles to understand the light related phenomena was completely dropped from scientific discussions. But then in the 20th century, Albert Einstein brought back the particle nature of light in order to account for a newly observed phenomenon known as photoelectric effect. So, photoelectric effect could be understood only through particle nature of light. But then Newton's particles, corpuscles, were attributed certain properties. Einstein's particles, photons, were attributed to certain properties, and the properties of a photon and the properties of a corpuscle are worlds apart. So, there is no comparison between these two at all. Therefore, the particle nature of light is also invoked to understand some of the phenomena related to light in the present times. In this session, we will be concentrating more on the wave nature of light and what kind of a wave light is, mainly because we would like to demonstrate that some of the properties that we discuss later on, which are part of class 10 science syllabus, like reflection of light, refraction of light, dispersion of light, interference and diffraction and so on, all these can be understood fairly well by using the wave nature of light. A general description of a wave is that it is a travelling disturbance. Now, the disturbance has to be scientifically understood in this context. By disturbance here what we mean is that it refers to a change in some physical quantity of the system. Now, this physical quantity could be position, as in the case of a simple pendulum. So, let me demonstrate that with a simple pendulum we have here. So, we have a pendulum here, and the bob of the pendulum is at a particular position. Now, when we drag this bob to some other position, now the position of this bob has been shifted. So there is a displacement. So this displacement is one of the physical quantities that can be disturbed in order to produce a wave. But before we actually go to a wave, let us try to understand with a single pendulum here, when we disturb the position and let it go, you see that it executes a to and fro motion, and it repeatedly comes to the mean position and it goes to the extreme position from where it was released first, and again it goes back to the mean position and it goes to the extreme position on the other side. So with the time there is a displacement which is continuously changing with respect to the mean position. So this is one of the physical quantities that can be changed. Now when you have just a single system like this, a pendulum, you call that an oscillator. Now as the pendulum is set into oscillation, we find that there is a continuous change of potential energy into kinetic energy and kinetic energy back into potential energy, all right. Now this is a single oscillator system. So now if I have to tap the energy that has been invested into this pendulum, you must know that I have spent some energy in drawing it from the mean position to the extreme position. So whatever energy I have invested into this pendulum, it translates into this oscillatory motion. Now how do I get energy out of this pendulum? Now one way is to use another pendulum, and I am going to put this pendulum at some distance from this. So now we have two pendulums here. So let me set one pendulum into oscillation and observe what happens to the other pendulum. So the other pendulum, which was at rest to start with, also gains energy, and the energy for this oscillation basically comes from the other pendulum into which I invested some energy. And along with the transfer of energy, there is also a transfer of momentum, because momentum is the product of mass and velocity, as you know. So what we have done in this particular case is that we transferred energy from one pendulum to another pendulum. Now you imagine a system in which you have thousands of pendulums which are connected to the same thread as you see here. Now it is possible in principle to set one of the pendulums into motion and then transfer that energy into all the pendulums. Therefore, we have now from a single oscillator system gone into a system where you have a large number of oscillators, and the energy from one oscillator is being continuously transferred along the whole system, and this transfer of energy is what you call a wave. So a wave has been set up by using a number of oscillators which can carry energy from one to the next, and this was made possible by causing a change in the displacement or by changing the position of one of the pendulums in that particular system of pendulums. So this is one of the physical quantities that you can change in order to set up a wave. So in order to have a wave, you can think of a number of pendulums being connected somehow or the other, such that energy is transferred from one to the other. Now the example that we have just now seen in the case of pendulums, we set up a wave which is a mechanical wave. So a mechanical disturbance is responsible for the propagation of this energy and momentum, and what we have is a mechanical wave. So just as you have a pendulum as an oscillator, you can also have oscillators of different kinds. One other kind which might be familiar to you is a spring to which a mass has been added. So again, the mass is in some equilibrium position to start with. So now if I were to gently displace it from that equilibrium position, and release, the spring mass executes a to and fro motion, and this is also a kind of oscillation. So again, you can have similar spring mass oscillators of a number of in a large number, and you can somehow, there are different methods of doing it. So you can somehow connect them in such a way that energy and momentum of one spring mass oscillator is transferred to others. Now another change in physical quantity that also results in a wave is very familiar to us, especially for people who are in Bangalore. Whenever there is a depression in the Bay of Bengal, when the pressure above the sea goes down, then you have not only cyclone in that particular place, in places like Chennai, but there will also be formation of clouds over Bangalore city, and you will also find that it rains for as long as the depression in the Bay of Bengal remains. So what has happened in this case is that the change in the atmospheric pressure, over the Bay of Bengal has been communicated over large distances of something like 300 kilometers, and when the pressure goes down in this location, there would be formation of clouds and there would be rains. In fact, the change in the pressure from the atmospheric pressure is hardly 10 to 15%, which actually brings about these cyclones. So we can think of this motion of air on account of pressure difference from Chennai towards Bangalore and also causing a low pressure here as a kind of a disturbance which has traveled all the way, and that is also a kind of pressure wave. Now a pressure wave is something that we create all the time on a micro scale or on a nano scale, if you like. As I speak now to you and you are hearing the sound, small pressure changes in my voice box is actually responsible for producing sound of a particular kind. And whatever the sound pressure wave difference, whatever the air pressure difference that I create in my voice box is communicated all the way, and if you are to be in this particular classroom, then that would be impinging on your ears. So the pressure wave pattern that I created in my voice box is exactly imitated by the eardrum in your ear, and the brain has evolved to interpret this as some meaningful sound. Therefore, creating a pressure difference and communicating the pressure difference is happening all the time as long as we are producing sound. But in the case of a cyclone, it is an extreme case of a pressure difference which is communicated. So sound wave is also caused by a disturbance in the air pressure within our voice box. Of course, the mechanism is a lot more complex than I am mentioning to you, but it is a fantastic mechanism to study from a physics point of view. There are a lot of resources that you can refer to. So sound wave is also a mechanical wave. Now before I go to the next example of how a wave can be set up by causing some disturbance in a system, there is one common point of observation between the example of the sound wave being produced by causing changes in air pressure and the transfer of energy and momentum that we discussed in the case of a series of pendulums. So when you have a series of pendulums and you disturb one of them, all others will get disturbed. So there is a transfer of energy. One very important point of observation is that whatever the direction in which you cause the disturbance, or whatever the way in which you disturb the first oscillator, the first pendulum, then all other pendulums will mimic the motion of the first pendulum. Similarly, when I speak a sound, when I produce sound of a particular kind, there is a particular type of air pressure pattern that I create in my voice box, and that is exactly the pattern that is regenerated by the eardrum. And this is a very important point, as we shall see a little later, but at this point I would like to mention that the source which creates the disturbance and which is transmitted all along the system, and the detector such as the ear or the last pendulum in the series of pendulums. Of course, every pendulum is a detector, but in this case I just take the end point at every, so the end points where they are detected, the detector will exactly mimic the motion of the source. Now another example where in which a change in physical quantity would bring about a wave, which is transfer of energy and momentum, is on a grand scale that happens on the earth. It is the movement of, it's a movement of plate tectonics. So you know from your geography classes that whenever the plates in the earth's crust, they slide one over the other, very often this causes vibrations, and these vibrations have enormous amount of energy, enormous amount of momentum, because the mass involved is very large, and by moving these huge masses even by a small amount will mean that there is a huge amount of energy and momentum involved in this. So when these plate tectonics slide over one another, it causes vibrations in a particular place where this occurs first. This place is known as the epicenter, and from the epicenter these vibrations are carried out in all the directions along the earth, and the seismic stations which are located on the surface of the earth, they pick up these vibrations, and from these vibrations it is possible for us to reconstruct how the originally vibrations could have been set up. Like I told you, in the case of a sound wave or a series of pendulums, the detector imitates the source as far as the vibration pattern is concerned or the pressure wave pattern is concerned. In the case of earthquakes, which are brought about by this motion of plate tectonics with respect to one another, whatever the pattern of vibrations that were caused at the source will be the pattern that will be recognized by the detectors. Of course, from the epicenter to the detector there could be a long distance, and along this distance, depending on the properties of materials of the earth in between the epicenter point and the surface, there could be variations, but we have enough scientific knowledge to reconstruct the mechanism that would have actually started this vibrations on a large scale. So this is what we call a seismic wave or an earthquake. Most of the times we look at this seismic wave or an earthquake as a kind of a destructive phenomenon, because we see properties of people being destroyed, and a huge loss to economy, because the roads and a lot of infrastructure would be damaged because of the earthquakes. But then if you remove the human property from this particular scenario, this way of thinking, and if you just look at it from a scientific point of view, this seismic wave or an earthquake is a wonderful opportunity for people who study the earth, especially the internal structure of the earth, how the earth is made up of and what materials go into making the earth and so on. There is no way of digging so deep and finding the material properties. So very often the seismic waves which come from the epicenter to the surface, they carry all the information about the medium in between. Therefore, by studying the wave at one receiving end, it is possible to guess intelligently with a lot of other resources. It is possible to guess intelligently what kind of a wave could have been set up originally at the source. Now my final example of demonstrating how a disturbance can cause a wave is a very interesting one, and also it is something that is familiar to you. So we have magnets here which are connected to a fidget spinner. Of course, fidget spinner you would have used in a certain other way, but here fidget spinner is very useful for the demonstration that we are going to have now. So there are these magnets which have been attached to each of the fidget spinners. So now you know that each magnet has a sphere of influence which is called a magnetic field. So if you take even as a simple magnet like this, it has a sphere of influence called magnetic field. Similarly, another magnet, this also has a magnetic field, and when these two magnetic fields are brought in some proximity, then you find that they interact. So one magnet is attracted to the other, so there is motion. So from its rest position, the magnet has actually gone up and got attached to the other magnet, all right. So magnetic fields can influence one another, and from rest position something can be set into motion. So we have three magnetic oscillators here, so to say, and they are all connected to a fidget spinner. Now the fidget spinner is being used only to get the circular motion in a very smooth manner. So if I were to now disturb one of them, you find that the other two also get disturbed. Now the way I disturb the source, I call this the source, the way I disturb the source, at the other end the detectors also mimic the same motion. Therefore, in all our examples we have seen that in whatever manner the source vibrates or oscillates, it is the same way in which other oscillators which are somehow connected also imitate. They also oscillate in the same manner. But the interesting thing is that for a magnet you do not need any connecting medium. In the case of the pendulum, we had a thread. I can show you that. So in the case of this pendulum, so we have this thread which is connecting these two oscillators. So this acts like a medium to propagate the energy from one oscillator to the other oscillator. In the same way, we do not find any connecting thing here, but still there is a transfer of energy and there is a transfer of momentum. This is because the magnetic influence does not require any kind of a medium. In fact, if you were to do this experiment in space, in perfect vacuum, you will find that the behavior is unaltered, only because magnetic field influences can actually happen even in vacuum or even in deep space. But what about the sound waves? So in the case of a sound wave, between my mouth and the ear of the listener, all the air molecules that are there in between us act like the simple pendulums, they act like the spring mass that I showed you, or they act like these, I can't say these exactly because they can transport even without any medium, but in the case of spring mass or the pendulum, or the seismic wave for example, we find that a medium is necessary. But there is one example where a material medium is not necessary, so even through space magnetic field can influence very easily. So through all these demonstrations and examples that we discussed, one thing that is clear is that to produce a wave, a disturbance is necessary, and what is propagated as a wave is actually the disturbance that we originally created, and what is carried away by a wave is the energy and the momentum that we invested into the system. So these are the broad ideas about a wave. So that brings us to the question, what kind of a wave is light, and what kind of a disturbance would actually result in the production of a light wave, and once produced, how would the light waves actually propagate? So these are the questions that we will be addressing now. Now for a long time people thought that light was a longitudinal wave. So you know longitudinal wave from your discussion about sound in your earlier classes. So in a longitudinal wave, as you as you can see in a slinky like this in the window of the screen, as an inset we are showing that a disturbance in one direction that you cause will be transported all along the slinky in the same direction. So that is a longitudinal wave where the direction of disturbance and the direction of propagation is the same. Now this happens very easily when the medium is very flexible. We will come to other kinds of waves as we discuss the ideas further. Now the other kind of a wave that is perhaps familiar to you, perhaps not. So I will spend a little time on developing the idea. Now this is known as a transverse wave. Now in the case of a transverse wave, the direction in which you cause the disturbance, that is you set the first oscillator into motion, and the direction in which the disturbance travels will be perpendicular to the direction in which you cause the disturbance. So this is a transverse wave. Now I have here two demonstrations to show you what a transverse wave is. So this is one of the demonstrations to show you what transverse wave is. So here we have a number of aluminum pipes which are all connected through a wire. Now if I were to take the one oscillator at one end, so each of them is like an oscillator here. So if I take one oscillator at the end and then I move this up and down, you have to observe two things. One, what is the direction in which other oscillators respond to this, and secondly, what is the direction in which this disturbance is traveling. So you find that whatever the kind of disturbance that I am showing, it is mimicked by each and every oscillator which is connected here. So this is the point I was trying to mention and try to generalize, and this is a very important point, that the source is imitated by all the other detectors. So each pendulum, each oscillator here is like a detector, and it imitates the pattern of oscillation of the source. Now we are moving this oscillator up and down, but then the disturbance itself is moving all along this line, and this kind of wave propagation is called a transverse wave. So wave is when you continuously set this oscillator into motion, all right. On the other hand, you can also just have a pulse. So a pulse is you just give a sharp tap to this, and you find that the wave propagates, the disturbance propagates. But actually what is being propagated is the energy and the momentum change that I brought into the source by lifting this up and down. So that is what is being transmitted here. So this is a transverse wave. So we saw how a transverse wave is set up and how a transverse wave propagates and how it is different from a longitudinal wave. So you can see the same thing even with a slinky in the following demonstration. Now compared to the longitudinal waves, transverse waves need medium that are comparatively very stiff. They have to be comparatively very stiff. So for the setting up of transverse wave, you need very stiff medium, which means very rigid medium, and this has a very important consequence in the context of light a little later on when we bring back this point. But for the time being, please remember that longitudinal waves by and large can be propagated through medium that are very flexible, and where the medium is very rigid, transverse waves can also be set up. It was Augustine Fresnel and Arago, two great scientists of the 19th century, who first showed through one of them, Fresnel through theoretical work, and then Arago through his wonderful set of experiments, they demonstrated that light is a transverse wave. So for the remaining part, we will see how it was shown that light is actually a transverse wave, because some of the great minds before this time, before Augustine Fresnel came into picture, it was believed widely that light is a longitudinal wave. So, to jump from one kind of an idea to another kind of an idea which are very different is always a very important step in the progress of science, and it is important to very clearly show why one is right and the other one is not right. So, Augustine Fresnel around 1817, so the beginning part of the 19th century, showed theoretically that light is a transverse wave. So, here is one of the experiments which actually historically influenced both Arago's thinking as well as Fresnel's thinking into light being a transverse wave. So, this is a transparent material, it is called calcite. Calcite is a crystal of calcium carbonate, and this is another transparent material, it is a ordinary piece of glass. Now, I am going to place this piece of glass on a sheet of paper, on which a line is drawn. Now, when you see the line through the glass, when you see that line drawn through the glass, you cannot make out any changes there. So, the line remains as it is. Now, when the same line is seen through this crystal of calcite, you will see that instead of one line, there are two lines, and as I gradually rotate this crystal, you will find that the two lines merge at certain orientation and they become one. And if I continue to rotate like that in the same direction, I will find that again I get back my two lines. Now, why did this line split up into two lines? It is the same thing that happens when you shine light from a laser source through the calcite crystal. You will actually see two beams being formed when it passes through this calcite at certain angles. Now, Fresnel and Arago argued that this can happen only if light is a transverse wave. It is a little beyond the scope to explain how this conclusively shows that light is transverse wave, but we can use the fact that longitudinal waves will always be in the same direction of the disturbance, the propagation will be in the same direction as the disturbance. Therefore, at all angles, at all orientations, we should be seeing just one path of light. But the fact that there are two paths of light is telling us that light is propagating in two different directions when the calcite crystal is oriented in a particular fashion. Now, for this to happen, longitudinal wave cannot be a possible explanation, therefore, transverse wave comes into picture. Just this demonstration is not enough to put 100% confidence to say that it is transverse wave. Therefore, we will have another demonstration here to show the transverse wave nature of light. So, we take a source of light and then we have two transparent materials here. It is the same material, in fact, I have two sheets of this. These are called Polaroid sheets. So, these Polaroid sheets, they in some measure have the same property that calcite crystal shows, because of which the path of light, you find two paths of light inside the crystal. Now, both are transparent. So, let me do this experiment in a couple of steps. So, first, this is the light source without this. So, now I put this transparent material there. Now, no matter how I rotate this transparent material, you always see the same amount of light passing through this, and you are seeing that on your screen. Now, I bring a second one and I place it parallel to this, except for a small intensity difference, you can still see the light coming from the bulb, right. So, now observe what happens as I gradually rotate this by small angles. Observe what happens to the intensity of light. You see that it is continuously diminishing, and when I have rotated the second sheet by 90 degrees, almost all the light is extinguished, almost all the light has been blocked. Therefore, what does this experiment tell us? This experiment tells us that somehow the propagation of light through some transparent material depends upon the orientation in which that material is held in the path of light. Now, this can happen only if light is a transverse wave. By the way, this particular phenomenon that you have just seen is called polarization of light, which would be dealt with in your college physics courses, but here you can just see what that polarization of light means. So, light is very sensitive to the orientation of this. So, if I go on further, rotate by 90 degrees, I find that all the light is back, and once again by 90 degrees all the light is blocked. So, every 90 degrees you find that light is almost completely blocked. Now, this demonstration is a very clear indication that light is a transverse wave. So, this was the first argument as to why light is a transverse wave. Now, any discussion of a wave brings in its wake two important questions. One is about its propagation and other is about the disturbance. So, right at the beginning of this session I mentioned that a wave is a travelling disturbance. So, some physical quantity has to be disturbed in order to set up a wave. So, we have just now seen through the experiments involving calcite and the Polaroid sheets that light is a transverse wave. So, this is as far as the propagation is concerned. Now, we come to the important question as to what has to be disturbed in order to produce a light wave. Now, this is a very hard question and it has its own historical development of ideas which contributed finally to recognizing the exact mechanism by which light wave is produced. So, work spanning over a couple of centuries, important experiments spanning over a couple of centuries, and very significant ideas that have been developed over a period of couple of centuries, or by a number of great minds, have all gone into finally answering the question, what is a physical quantity that has to be disturbed in order to produce a light wave. So, let me take you through a few of the significant experimental ideas that people came up with which finally helped us answer this question as to what has to be disturbed in order to produce light. So, one of the first ideas which goes into answering this question is due to a wonderful experiment due to Hans Christian Ørsted. He performed this experiment a couple of years after Fresnel's work in 1817. Remember, Fresnel proposed the theory that light is a transverse wave, and just a couple of years later Hans Christian Ørsted did this fantastic experimental demonstration, and let me first demonstrate the experiment and then get into the details. So, in this experiment that originally Hans Christian Ørsted performed, we have a magnetic needle which is surrounded by several turns of a copper wire here, and the wire is connected to a power source which gives us a large current through the circuit. So, to start with, observe that the needle is in an equilibrium position, it is undisturbed, and it is not disturbed by any kind of air currents. So, you should be clear about this. When you do experiments, you have to take care of these things, because finally you have to attribute the cause of whatever you observe in an experiment to specifically certain factors. So, you have to be very careful about those things. That is the reason why this magnetic needle has been kept inside a glass case. So, now we switch on the power supply, carefully observe the position of the needle. So, as soon as I switch on the power supply, there is a current that flows through the coil, and the magnetic needle is slightly displaced. So, it rotates by a small angle. So, I switch off and I switch on again to show that the magnetic needle is affected by the current flowing through this wire. Now, you know that a magnetic needle is made of a magnetic, it is a magnet actually, and for a magnetic needle to be displaced or deflected or disturbed, you need another magnet. But we have nothing like that. You know that copper is not a magnetic material in the normal sense of the word we understand. That is, a piece of copper is not attracted to a magnet. Therefore, how can this piece of wire through which current is flowing affect the position of the magnetic needle? So, this experiment actually demonstrates that there is a magnetic influence that is created when current flows through a conductor. This is a significant experiment by Hans Christian Ørsted. Now, for the time being, it may look like this has nothing to do with light, but very shortly we will see the grand connection between this experiment and how exactly we produced a light wave. So, the next significant experiment which helps us to answer the question how light wave can be produced, that experiment can be attributed to Michael Faraday, a genius experimenter. He did fantastic number of experiments, and each experiment had a big impact on the growth and development of science. He not merely did experiments in the field of physics involving electricity and magnetism like most textbooks portray, but the less known phase of Faraday is that he did phenomenal amount of work in chemistry also. In fact, it's a perennial fight between physicists and chemists whether Faraday should be classified as a physicist or a chemist. But then Faraday, being a great thinker, he was a philosopher and he belonged to all disciplines of knowledge, including physics and chemistry. So, this is the experiment which was performed by Michael Faraday, and in this experiment we have a galvanometer. A galvanometer is a device that detects current when it passes through this device, and it is connected to a coil of wire. There is no power supply connected here, unlike in the previous experiment of Hans Christian Ørsted. Instead, we have a piece of magnet here. Now, this piece of magnet is now moved through the copper coil, and you will observe that the needle deflects every time there is a motion of this magnet inside the coil. Every time the magnet moves inside the coil, the galvanometer needle deflects. Since galvanometer responds to electric current, it is an inference that the motion of this magnet into the coil is generating current somehow. Now, putting the two experiments, this Michael Faraday's experiment and Hans Christian Ørsted experiment, we come to a very, very important idea, that is, electricity and magnetism are related to one another. Until the demonstration by Ørsted, magnetism and electricity were treated as two separate entities, and this particular experiment by Faraday very firmly established that electricity and magnetism are related to one another. Of course, Faraday went on to do many more experiments related to electricity and magnetism, all of which showed that one can generate magnetic effects, a magnetic field using electric current. That is what happened in Ørsted experiment. Or you can generate current by using magnet. more precisely by moving magnets into a coil or in the vicinity of a conductor, a good conductor of electricity, you can generate current. Therefore, you can generate electricity with magnetism, you can generate magnetism with electricity, and this is a fantastic period of scientific activity as far as physics is concerned. The early part of 19th century, Fresnel comes up with the theoretical background for light wave, and then Faraday and Oersted are doing experiments showing the relationship between electricity and magnetism. But still the connection between light and electricity and magnetism was yet to be firmly established. But even in this particular period, when people did not know the relationship between electricity, magnetism and light, Faraday went on to do an experiment, and even to this day I do not know what was the motivation for Faraday to do this experiment, and only a Faraday can come up with an experiment of this kind. What did he do? He took the Polaroid sheets that I demonstrated earlier, the Polaroid sheets like this, and then you have a certain orientation through which light does not pass at all, okay. And what he did was, between these two, he subjected light to an extremely strong magnetic field. So where no light was expected, some light passed through this Polaroid sheet, which showed that the propagation of light, the direction of propagation of light is affected by magnetic field. This is one of the most fantastic experiments that Michael Faraday did at a time when the relationship between light and electricity and magnetism was not known. But this has played a very significant role later on in the development of the idea of the light waves. Next important question, development in answering this question as to what has to be disturbed to produce light wave was given by James Clerk Maxwell around 1864. So James Clerk Maxwell, while working on electromagnetic waves, he was working out the theory of electromagnetic waves, and in the process he found out that all electromagnetic waves, when they travel in space, they travel at a speed of 3 lakh kilometer per second. Now this number 3 lakh kilometer per second must ring a bell in your mind now, just as it rang a bell in the mind of James Clerk Maxwell at that time, because this 3 lakh kilometer per second happens to be the speed of light. And before long before James Clerk Maxwell's work, a Danish astronomer by name Ole Romer had done some astronomical observations. This was related to the timing of eclipse of a satellite of Jupiter called Io. So he was calculating the eclipse timings of Io according to certain laws of physics, and then he was also observing the time at which the eclipses occurred, and he did this over a long period of time, and he found out that there was a systematic variation in the difference between the calculated time of eclipse and the observed time of eclipse of Io by planet Jupiter. And it's another long story. The end result of this observation was that the speed of light is nearly 3 lakh kilometer per second. Now James Clerk Maxwell theoretically shows that electromagnetic waves travel in space at the speed of 3 lakh kilometer per second, and you are observing eclipses like Romer did, Ole Romer did, from the light that you receive from Jupiter, the light that you receive from Io. Therefore, there was for the first time a kind of a connection between these electromagnetic waves and light. So James Clerk Maxwell's work showed that light waves are actually electromagnetic waves. Now this is an important step. One more important step closer to getting the answer to the question, what should be disturbed in order to produce light. So, I will summarize here at this point quickly. So, light wave is a transverse wave, Fresnel shows this, and the fact that it is a transverse wave is shown through certain experiments through calcite, and when light passes through calcite and other materials like this Polaroid sheets. Then there is this connection between electricity and magnetism established by great experiments by Oersted and Michael Faraday, and now Maxwell says that there are electromagnetic waves, and electromagnetic waves move at the speed of light. So, putting all these things together will tell you that light must be a transverse electromagnetic wave. Now, how do you produce electromagnetic waves? So, if you can answer the question how electromagnetic waves are produced, then it is easy to answer how light waves are produced, because light waves are most likely electromagnetic waves at the time James Clerk Maxwell discovered this. Could that just be a kind of a coincidence that electromagnetic waves have the same speed of propagation as that of light? It could very well be. There are so many numbers that come out coincidentally. This also could be one. So, it is very important that we measure the speed of light very precisely through experiments. After all, we had just one experimental observation by Ole Romer, and that itself could not be taken for granted that speed of light is exactly that much. So, you have to do experiments in a laboratory to find the speed of light. In 1848, so this is around the time when Faraday is doing some experiments in electromagnetism, Oersted has already done something, and James Clerk Maxwell is beginning to work on theory of electromagnetic waves. So, there is a flurry of activity, scientific activity, intellectual activity pertaining to electricity, magnetism and light. So, in 1848, around that time, a French experimenter called Fizeau, he does a fantastic experiment to measure the speed of light, and he measures the speed of light not indirectly as Ole Romer did, he measured it directly. So, he finds out the time taken by a pulse of light to go to a particular distance and then come back. So, by timing the distance travelled by light and knowing the distance travelled by light and also finding the time, you can get the speed by simply dividing distance by time. Nothing can be a more direct method of measuring speed of anything, and Fizeau's experiments clearly showed that light does move at a speed of 3 lakh kilometer per second. So, there was no doubt now that these light having a certain speed and electromagnetic waves also having the same speed was not just a coincidence, because the experiments showed that. But still it was not enough. Still it was not enough, because Fizeau's experiment again shows that the speeds are matching. It does not tell you that light is an electromagnetic wave. But like they say, there are certain periods in historical development of ideas that a number of great minds work on different things, and somehow they all fall into place when you look at the grand connection among all the different works by different minds. So, just when Clerk Maxwell had completed his theoretical work on electromagnetic waves, a German physicist by name Heinrich Hertz, he does a fantastic experiment to produce electromagnetic waves experimentally. So, this is the first instance of producing electromagnetic waves intentionally in a laboratory experiment. So, he does that, and now if you go back and see what exactly was the mechanism by which the electromagnetic waves were produced by Heinrich Hertz, then you know the answer to the question, what should be disturbed in order to produce light waves. Then it turned out through some other work by scientists that light waves are produced by causing a disturbance in electric charges. Now, electric charges have electrical property, they have an electric field. Now, light does not seem to have any connection with electric charges. Now, this is the beauty of the whole process of scientific investigation. So, gradually we have established connection between electricity and magnetism, and then we have shown that there are electromagnetic waves which move at the speed of light, and then electromagnetic waves have been produced experimentally, and in order to produce these electromagnetic waves, Heinrich Hertz at a fundamental level resorted to displacing electric charges. So, we will not go into the details of Heinrich Hertz's experiment, it is slightly beyond this particular session, but it is a beautiful one and you can read and understand, try to understand. But the essence of that whole experiment is that if you take an electric charge has a sphere of influence called electric field. Now, if you shake the electric charge up and down, for example, you are disturbing its position. So, as you change the position of the electric charge, the electric field associated with this will also change along with the position of this charge. Just as in a simple pendulum, as the oscillations go by, the amplitude of the oscillation continues to change gradually. In the same way, the amplitude of this electric field, the strength of this electric field gradually changes as you shake an electric charge. And it is shown through experiments again that whatever the direction in which you shake the electric charges vigorously, you set up a wave of light in a direction perpendicular to that. Therefore, all these things tell us that light wave, in order to be produced, electric charges have to be oscillated, but then it is not as easy to oscillate electric charges at that rate as it is, for example, your vocal cords to produce sound waves. Your vocal cords vibrate typically a few hundred times to a few thousand times per second. Even that is a huge number actually, but that is possible humanly. It is possible by all the animals. But then when it comes to electric charges being oscillated, to set into oscillation to produce light wave, you have to oscillate this something like 10 billion times in 1 second, okay, 10 billion times. So, a billion is 1 followed by 9 zeros. So, 10 billion is 1 followed by 10 zeros. That many times you have to move a charge up and down in 1 second to produce light waves, okay. But there are light waves of different kinds, and for that you have to take electric charges and move them at different rates. So, these will form and how these are formed, how these are achieved is something that would be discussed in our next presentation. So, to wind up this presentation, we see that a light wave is a transverse wave, it is an electromagnetic wave, and it moves at the speed of light, like all electromagnetic waves. So, more details about the properties of light such as reflection, refraction and others in the following sessions we will be taking up, but for all that, this fundamental idea about what kind of a wave is a light wave is absolutely essential to be understood, and that is why we had this particular session. So, what we have tried to do in this particular presentation is not only to answer the question what kind of a wave is light, but as young students of science, you should also know that the production of the progress of a particular scientific idea does not happen overnight. So, we borrow ideas from every other's work. So, in this case we have seen how Newton, Huygens, Thomas Young, Romer, Fresnel, Arago and Faraday, Maxwell, Hertz. I mean, I have left a number along the way. This is my incomplete list, and even that is pretty long. So, we borrow work from all these people done over a long period of time, and then science has a way of integrating different works done by different people at different times and integrating them into one significant piece of knowledge. So, in order to answer this particular question, there has to be a good deal of development in understanding electricity, in understanding magnetism, and then experiments to measure such great speeds that we see. So, it is all very, very exciting. So, we hope that you have enjoyed this session. So, if you have any feedback about this session, so kindly do email us to the email ID that is mentioned here. So, thank you very much.